Okay, guys, today we're going to be talking about CPX valve terminals from Festo. And just to start off the bat with some general overview information, we have Festo has three different types. There's polymer, standard, and then we've got metal for like the automotive, and then there's a light or the polymer type. And there's different advantages and disadvantages to each, which is why they're made, of course. And today we're going to be talking about diagnostic options when connected to a Allen Bradley PLC using Rockwell software. So we need to get diagnostics from the FB36 to the PLC. And the first point I want to make is regarding the CPX Festo valve terminal itself. Okay, if we zoom in here, this is just a picture from the software. We've got an FB36 module, we've got a 16DI, which is a digital input module, an 8DI-DO, which is 8 digital input and digital output, and then we've got a 4 analog input module. Okay, it's really important to understand that when there is a fault on a module or the FB36, more so the modules to the right of the FB36, when there's a fault, this CPX valve terminal has a C bus. So there's a bus or a backplane with a bus operating on it called C bus, and if the 4AI or the 8DI or the 16DI all have individual faults or short circuits or whatever you want to call it, any type of fault, that fault is transferred across the C bus to the FB36. And if the PLC program has not programmed any faults that are gathered from the FB36 to the PLC, then those faults will remain at the FB36. You'll have some LED status to look at. You'll be able to log in with the Festo maintenance tool software and look at the faults while on. The problem is that the FB36 manifold could be completely frozen, and if you don't monitor the diagnostics of the FB36, then the connection can still be active and think that there's nothing wrong, and therefore, you know, you could have a crash on the machine, you could have anything going on. So it's really important to set up diagnostics between the FB36 and the Rockwell PLC or the Allen Bradley software, or vice versa. Sorry, the Allen Bradley PLC with the Rockwell software on it. So that's what we're going to discuss today. And when we look at the FB36, there's a couple of DIL switches on it. Okay, there's DIL switch 1 right here, which sets up the communication mode. And when we're in this network layout right here, this is called remote I/O because it's a remote I/O device. And so we're going to use this operating mode right here. We're going to set up for Ethernet IP protocol because you can use Modbus with this particular thing, but we're not going to do that today. The next logical step is to set the IP address. In order to set the IP address, you can use the DIL switches here, and it will end up with a 192.168.1 dot, and then whatever the address is that you set here, from 1 to 255 or 254. And or you can set it up so that you can use software to assign that. And we're not going to get into that because there's other videos that cover that for the DHCP and bootp addressing. And then the more important thing we're going to discuss are what the diagnostic mode options are. So by default, the status bits or for remote I/O are turned off. So this DIL switch 2 right here, both switches will be down, and therefore you have 0 diagnostics working. Okay, which is, as I described earlier, that's a poor situation. Some applications might have that as an acceptable situation, but in 95% of the applications, you really need the diagnostics. And the first simplest diagnostics overall is what is called status bits. Okay, the status bits here, we have a situation right here where when we turn this on here, we have 8 bits input, 0 output, and what that does is it occupies 2 bytes and we only use 1 byte, and that's the design of the status. Okay, to go a little deeper into that, I'm just going to skip this page here. So the status bit basically serves as a common diagnostic message or global fault, and it's basically using this next page right here. So if I zoom in a little bit, this is all part of the user manuals. So we have diagnostics via field bus status bits, and if I go to the Festo maintenance tool software, which is downloaded from the Festo website, we have under system settings here, we have nothing here at all because we're offline right now. When we go online to the system here, then we have a couple extra tabs here, and we have a system status bit right here. So right now, if I go to my manifold and I short this manifold over here and I do a refresh, we'll see here that the fault source and the fault type. So the fault source is an input module. So if we go back to this right here, this is a module type, so error at input, and we have a fault type, and that's a short circuit because I'm shorting some wires out here, and there we have a short circuit. Okay, that's the error type. So without doing anything, we have a fault. We can look at that through the Festo maintenance software, but this is only going across the backplane to the FB36. Unless you set up the status to be gathered in the PLC, all that status information stops here at the FB36. So I'm going to show you that right now. So I have a PLC program here. I'm just going to go online. So what we've done here online here, or what I've done, is I've added this generic module here. And the generic module can be created in a variety of ways. You can import the EDS file using the EDS installation tool here, and you can configure very simply. You come down here, you see that there's 13 bytes of inputs, 3 bytes of output, and at that point you have some data running back and forth. In the second, more complicated situation, and there's YouTube videos on my channel for this, you can come up to here and do an export L5K, and you would export this, and then you do an import into here, and then you end up with this generic module here. Okay, it imports the instances here. So we have 13 inputs, we've got 13 outputs, which is this one here, and then we've got a 64-bit or 8-bit configuration. The configuration, when we use that, is very important, but that's covered in the YouTube videos for the import-export. Okay, when you do an export, typically you have to turn this unicast on if you're in an older Rockwell PLC because it's default off. Okay, you don't want to be you don't want to be multicasting messages. So once we have this connection in the controller tags here, we always have the gray tags, and it's created the data here. And the nice thing about doing the export from the Festo maintenance tool right here, this, and then importing into here, is that there are some descriptions here. So in my case, I've added a few extra descriptions to these first bytes, 2 bytes, both for inputs and outputs, because I have added, or because I've configured the 2 inputs here as STI, which is set up and not discussed yet, of course. I made a little mistake here, but what this does is it sets up everything, and when the interface is not being used, and I'll explain this after, when it's not being used to do IO diagnostic interface, then it's doing the same as the status bits here. So in my case, we have diagnostics data coming through on the first byte here, this E0 through E7 bits, and those bits there are being mapped in this routine here. Okay, it's being mapped to this status. The status, I've created a data type, which you don't have to do. All you have to know is what they're for. And like I said before, we've got faulted output, valve, input. Basically, I'm mimicking what I've got in the user manual right here. Okay, these bits. And once I have those bits, I'm copying them. Okay, and now this status bit here, you know, this is what I have. So right now I have a faulted input and I have a short circuit, just like I did in the Festo maintenance tool. Okay, so I have that status, and if we go and we look at the arrangement here, I'm looking at, this is the status bits again, combination, which I just showed you earlier right here. Okay, and what I'm doing here is, you know, I'm looking at the connection itself. So that's the Ethernet connection, making sure that it is faulted here. That's what this is looking for. And when it's not faulted, that's when I'm looking for the status. So I'm always looking for status because this information is always coming across, and based on the bits and the station power, then we will have a fault. So in this case here, I have a short circuit overload fault at an input module. Okay, and this code is very, very simple, and it's required. If you don't monitor this information here in your PLC code, again, as you can see here, I have no connection problem. If I was to pull the Ethernet cable off right now, you know, the Rockwell world shows an Ethernet problem. Okay, it shows you a connection timed out, but it does not show you faults of the FB36 manifold. Okay, if I plug the Ethernet cable back in, the fault's cleared, and yet we still have a short circuit. Okay, and if we didn't have this code, the short circuit would not be known, and the machine would still be thinking that the connection's okay and not know that there's a problem on the manifold. Okay, so this is a bare minimum to have the status information here coming back to the controller, whether it be a robot or a PLC. Now, the next DIL switch setting is going to be the IO diagnostics interface. This one right here. Okay, this one right here. Okay, the STI mode in the FMT is going to occupy 16 inputs, 16 outputs. Okay, and when we set the DIL switches like this, then we are going to skip over here, and when we do that, like I showed you before, you go to the FB36. This is the STI here, and let's just look at what this information does for us. Okay, so we've talked about the status bits already, the diagnostics coming across the backplane, and then the field bus collects the data. And when we look at the field bus interface, we have 16 bits of input, 16 bits of output, 2 bytes input, 2 bytes output. You know the math. Basically, what we have here is a more elaborate structure. So we have a little control bit right here, a couple of reserve bits, and right here we have in the orange a function number. Okay, so basically, if you move into the input area, we have an acknowledgement, this green one over here, and then we have a reserved area again, the purple, and then we have the diagnostics data coming back from the manifold, because this IO diagnostic interface is a read-only concept. Okay. If we go to the next little thing here, how does it all work? Well, it's pretty straightforward. What you do is you download the user manual. Okay, the user manual. When you open it up, it has okay, let me show you the user manual. There's a user manual for the Ethernet IP, the FB36, and then there's a system user manual. You kind of need both, and I'll show you that right now. So I'm just going to go to the website here. Okay, I'm on the website, and I just typed in CPX at the festo.com website here, and first thing we want to do is we want to download this system manual, CPX-system. Okay, it's pretty old because the CPX has been around for a while, and we'll click here and you'll download this and so on and so forth, and you end up with this system manual right here. Okay, I'm going to close that, and then as well you want to download the appropriate FB36 manual, wherever that may be. You can get a little more specific. FB36 downloads. User, and then we have this manual right here. So we would download this manual right here, and I'm just going to open those now. Okay, so I have opened the system manual right here, and I've opened the FB36 manual, and if we go through FB36 manual, let's see here, go to the diagnostics here, we have a diagnostics interface. So section 5.4 in this 2019 manual talks a little bit about the IO diagnostics interface, talks about the DIL switches, which we just discussed, and it talks about the rules for addressing. Okay, the system manual has the real detail. Okay, we have section 5.2, which is diagnostic via status bits or the IO diagnostics interface. There's your status bits here, and then we get into the IO diagnostics interface. Okay, so I've added my own notes to the PDF here, and there's a couple of samples in here on how to use it, and I'm going to show you that. But basically, going back to this right here, this is an overall chart on how to request a function. Okay, so the first thing you're going to do is set a function number, and that's in these 12 or 13 bits right here. The function number, that's where you go to the user manual. The user manual shows you the function numbers, which are in Appendix B. You can go down here. Today I'm going to show you 1937. You come over here, click on table B40, and it shows you that function number 1937 here, that bit 0 through 5 is the module of the first faulty number, and then we have a diagnostic status, and down here they're saying what it is. So basically you would put 1937 written in a binary format into this orange area here, and then you're going to turn bit 15 on. When you turn bit 15 on, bit 15 on the input data table is going to come back, which is your acknowledge 1 right here. Then the data that has been requested will be in these 8 bits right here, the green, the accept data. In this case here, bit 0 through 5 is where there's going to be a value, and what we do next is we turn off bit 15, which is this, we're canceling the request, and then you'll get a handshake on the 15 to say that the handshake's complete. And that's the gist of it. It's not that difficult. It's quite user-friendly. It's really important to understand that, which I've written in red down here, that when bit 15 is turned off, that this data area down here is acting identical to the status bits right here. Okay, so in my code here, I'm basically looking at this information here only when I have no no execute turned on, or no control bit. Okay, so this right here is function number 1937, and because of where the bits lie and so on and so forth, I'm just going to set a value here, 1937, and then I'm going to take that value and I'm going to extract it into the bits. Okay, this is basically a bit distribute, and I'm basically taking it, portion of this value, which is the 16-bit number, and I'm putting it into the raw data area here. So I'm basically shoving it, the whole value, I'm taking part of the integer and taking it and putting it into this first output byte, and then the next part I'm going to take and only put these 5 bits in. Okay, that's what this does, this and this and this. So the idea here is that I do an execute request. That's just a programming bit. I make sure that I have a connection, of course, to this right here, and when this is all done, then I'm going to turn the control bit on. Okay, the 1.7 is me turning on this bit right here, because it's array number 1, which is the second byte, and I'm turning on the last bit. Okay, and for my own clarity, I've added a timer here just to see how long it takes to get some feedback. So basically, I'm going to turn this bit on, and then I will get an acknowledge. This is the E15, which is this bit right here, E15. It's going to come back and acknowledge the fact that I've done it, just like in this sequence right here. I'm going to get the acknowledge back, and that's me getting it. I'm just setting a bit, and I'm moving the timer value into the request time, so I know how long the request took place. And then, because of the user manual, we know that bit 6 indicates that if bit 6 is 1, there is diagnostic data. If it's 0, then there is no diagnostics data. So I'm basically saying here is, if bit 6 is on, diagnostics data is available, and I'm going to take the raw data value, which is, this is the raw data right here, the input table, the whole byte, and I'm going to copy that into the module with fault that I've created. Okay, so at this point in time, if I toggle this bit on, I'm sending this bit, I turn on the control bit, timer's timing, we had an acknowledge, and took 3 milliseconds. Or actually, it's smaller than 3 milliseconds, but, well, it is 3 milliseconds. And if I turn this off and keep doing this a couple times, we'll see here that it resets the code every time, and it's extremely fast, handshake wise and everything. and it gathers the data. Okay. If we go further into the manual, the next programming example I have is function 1938. So if I go back to the user manual here, 1938, which is this function right here. This one right here, function 1938. It's going to give you the current error number. So right now the current error number is 2, which is, with the description text is 2, which is short circuit. And in my code, if I go to my code here, open up this, and of course I can't have them both on. I'm going to turn this one here off, toggle that, Control T, toggle, Control T. So I'm just toggling that off and on, so we're turning that off, and now we're going to turn this one on here, and we execute this. We get a value of 2, because that is the value. And that is an example. Okay, so what I'm going to do here is I'll just try and create a few different errors here. So I'm going to remove the short circuit, because we've already seen that happen. And now I'm going to pull the manifold apart and try to create a bus fault here. Okay, I'm doing this live, which you shouldn't, and hopefully I don't blow something up. And there we go. So I've created a C-bus fault. And again, as I explained earlier, the C-bus fault is a backplane fault going across all the modules to the FB36. Okay, so I have this fault, and let's look what's happening in the PLC here. So as we see, the PLC, the connection to the PLC has no problem, which is correct. I mean, the FB36 module is not faulty. It's still communicating at its speed and at its requested packet interval here. Okay, so that's correct. Again, if you had no status faults and whatnot set up in the PLC here to be gathering data from the FB36, you would think that everything's working fine, which it's not. We expected it not to be. Okay, so if I go back to 1937 here, I'm going to go into this right here. I'm going to execute a request. The first thing we notice here is that we're not getting an acknowledge. Okay, because it's in fault. It's really confused right now. If we turn the execute bit off, and I've lost my page here, I need to go like that. Yeah, sorry. So all my bits are off, which means that my status is now active. If I look at my fault code here, I'm not faulted, because this here is monitoring the fault of the Ethernet IP connection, not the fault of the FB36. Only this code here is monitoring that. So if I scroll down here, you'll see here that I have a general fault at output, and we have a general fault at input, and we have a general fault at analog specialty module, because the whole bus is faulted. And what we can do here, which I didn't do yet, is we don't have to look at the bit level. If you want to be as general as possible, we can just do an online change here, and I guess it's add a not equal. So basically take this, get rid of that, so that we're just looking at the whole value here. I'm just going to copy this real quick here and call this, if it's We'll call this COM OK. So I'm going to say it is equal. If it's equal to 0, then we're okay. I'm going to say no faults. New bool assemble. So we have no faults. No, we don't. We have a fault because one of the bits in this whole array, or 3 bits, are actually turned on. So you can use that as a general overview, but again, it's really important to understand that without this dill switch setting here, without anything set up on this right here, without either the IO diagnostics interface active or the status bits active, you're not going to get any status, and you can have the FB36C bus with all the faults happening all the time, and you don't know anything about it in the PLC. Okay, so I hope this was informative and helps you understand how to use the IO diagnostics interface, and as well as the status. The IO diagnostics interface is probably the best because it has this extra functionality and it offers the status bits. So I hope this is good enough for an understanding.